In this presentation I'm going to try to explain this complicated looking expression here, which is the formula for the discrete Fourier transform. And the discrete Fourier transform is basically trying to analyze a signal x of n, which is a time domain signal, and determine the sinusoids that that signal is made up of. So all Fourier analysis techniques are trying to identify the sinusoid present in a signal. The DFT is the discrete version which deals with discrete signals. Now, first thing I'm going to do is try to relate this to a practical example. So I'm going to use MATLAB's built-in FFT function, which is its implementation of the DFT, and relate that practical example to this mathematical notation. So let's bring up MATLAB. And what I'm going to do is just create a time domain signal, which is just a sequence of random numbers. I'm going to make it 20 samples long, so these are my 20 time domain values. And to use the FFT in MATLAB, I just type FFT, and FFT stands for Fast Fourier Transform, which is just an efficient implementation of the DFT. So when I hit return, basically what's happening is the mathematical formula that you saw on the previous slide is just being implemented and applied to that signal, lowercase x. And the result of that has been stored in the uppercase variable x. And this is a convention used to use capital for frequency content and lowercase for time domain content. So x is our frequency content, or basically the magnitudes and phases of the sinusoids that make up the time domain signal lowercase x. And we see that x is just a sequence of complex numbers. So I have all these complex values returned by the FFT function. So basically the DFT, that's what the DFT returns, is just a sequence of complex values. Okay, and we can see here that I got 20 values in total returned. I'll just note as well that the time domain signal that I analysed also had 20 samples. So let's relate that to the mathematics. So I said I have a signal x of n that I'm analysing. There's a variable n which refers to the sample number. So that's the index into the time domain signal. I've also got this variable k, which is referred to as a bin number. And that's the index into the sequence of complex values that you saw returned by the FFT. Okay, and x is just a placeholder for our frequency content, the same way as that lowercase x is the placeholder for our time domain content. I've also got a capital N variable here, which refers to the sample number, or sorry, the number of samples. So that's the number of samples, which in our example was 20. So I think I have all the variables defined. What I'd like to do now is just try to get a better understanding of the equation and to appreciate what's going on. Now, most people, when they're looking at the DFT expression, have difficulty with this part of the expression, and that's referred to as a complex exponential. And complex exponentials can be difficult to visualize, and what's probably most convenient is to instead break it down into cosine waveforms using Euler's expression, which is this expression here. Now, Euler's expression can be rewritten as e to the minus x cos x minus j sin x. Okay, and what I'm going to do now is use this to expand out the expression so that it's something that we can relate to a little bit more easily, because we'll see then that it's sine waves and cosine waves rather than dealing with complex exponentials, which are again difficult to visualize. So let's rewrite that expression using Euler's formula. So x of k is equal to the summation between n equal to 0 up to n minus 1 of x of n, which is the signal that we're analysing, which is multiplied then by cos omega kn, minus j times the summation of n equal to 0 to n minus 1 of x of n, the signal that we're analysing, being multiplied by a sine wave, omega k n. Okay? And now we see that all that's happening really is that our signal that we're analysing, x of n, is being multiplied by a set of cosine waveforms, and it's also, the signal that we're analysing is also being multiplied by a set of sine waveforms, okay? And the result of that multiplication is then summed together. Now, that process where you multiply and sum is known as correlation. Correlation is a very well known signal processing technique. We won't be going into it too much, but just be aware that this is a particularly well known technique. But it measures the similarity of one signal with another one. So in this case we're measuring the similarity of the signal that we're analysing with cosine waveforms. And over here we're measuring the similarity of the signal with sine waveforms. Another way of thinking about it is that it measures the presence of one signal in another one. So when I think of the DFT, I think of this part of the expression as being a measure of the presence of a cosine waveform in the signal x, and over here it's a measure of the presence of a sine wave in a signal x. Okay, so we'll say that correlation is a measure of the presence of one signal in another. And what's happening here is the measure of similarity, or the measure of the presence of the cosine waveforms, is being stored in real numbers, and the measure of the similarity of the signal with sine waveforms is being stored as in an imaginary number. Okay, well, at least as an imaginary term. So we can see that the complex values that we get back are really a measure of similarity of the signal with cosine waveforms and sine waveforms. That's really what we're seeing when we apply the DFT. Now I have a figure which hopefully illustrates this process a little bit more clearly. Before getting into that, I just want to expand out this expression a little bit more so that we have a bit of an understanding about what we'll see in the figure. And all I'm going to do is substitute omega k here for its defined value, 2 pi k over capital N. And remember that capital N is the number of samples in the signal that you're analysing. So it's a summation between between n equal to 0 and n minus 1 of x of n, the signal that we're analysing, by cos 2 pi k n over capital N. Well, it's j times the summation of n equal to 0 up to n minus 1 of x of n by the sine of 2 pi k n over capital N. Now, what I really want you to understand now, what I want you to focus on, is on what this represents. Okay, and remember that x of k is evaluated for different values of k, so it's evaluated for k equal to 0 up to k equal to n minus 1. That's what it's evaluated for over that range of values. When k is equal to 0, let's take a look at this expression. When k is equal to 0, that's equal to 0. All of this is equal to 0. So really what we have is the cos of 0, which is equal to 1. So that expression becomes the summation of n equal to 0 up to n minus 1 of x of n multiplied by 1. Now, when k is equal to 0, the sine part becomes 0. So the j part all becomes 0. So that's minus j 0. So really x of 0, capital X of 0, is equal to that. Okay. Now, the other cases are more interesting in some regards. So, I mean, the cases where x is non-zero. So, when x is equal to a non-zero value, we're still multiplying the signal that we're analysing by this expression. And what I want you to do is understand what this expression looks like. And a cosine waveform, or this expression, when k is equal to 1, will be a cosine waveform with one cycle over n samples. When k is equal to 2, we will have a cosine waveform with 2 cycles over n samples. When k is equal to 3, we'll have a waveform that has cosine waveform which is 3 cycles over n samples, and so on. So in each case we have a set of cosine waveforms with an integer number of cycles over the n samples. For the sine wave case, it's very similar. It's basically just a set of sine waves. Sine waves start at 0, so we'll have a sine wave with 1 cycle over n samples. We'll have a sine wave with 2 cycles over n samples, a sine wave with 3 cycles over n samples. So it's the same situation, only we're dealing with sine waves rather than cosine waves. So now I'll just bring up that figure that tries to describe this process, and I'm going to use a few examples, and they're very basic examples, but they'll illustrate this whole correlation process. So remember, what I'm saying is that this part of the expression basically is a measure of similarity with a set of cosine waveforms, and over here we have a measure of similarity with a set of sine waveforms. And these measures of similarity indicate the presence of the sinusoid in the signal that we're analysing. So I'll just bring up the example now. Okay, there we go. So the signal that I'm analysing in this case is a well-defined signal. It's a cosine waveform of amplitude 2, and it's got 1 cycle over 8 samples. So I've got 0, I might change the colour there, make it easier to see. I've got sample number 0, 1, 2, 3, 4, 5, 6 and 7. So n is equal to 8, with samples labelled from 0 up to 7. Okay. Now, remember what the DFT is trying to do. It's trying to determine the presence of sinusoids in a signal. Now in this case, I've only got 1 sinusoid present. So if we were to think about the magnitude spectrum of this signal, what I'd expect then is a single spike to indicate the presence of a single sinusoid. Okay, that's what I expect. Let's see what the DFT gives us. Now this is just a visual representation of what the DFT is doing. Over here I have my what I call analysis basis functions. So analysis basis functions. And these analysis basis functions, you can see that they're all the sinusoids that I mentioned in the previous when I talked about the formula. I have a sine waveform with 1 cycle over the duration of the signal that I'm analysing, which is in this case 8. So I've 1 cycle over 8 samples, a cosine waveform with 1 cycle over 8 samples. So all down on this side I have my set of basis functions, and they're all cosine waveforms and sine waveforms with integer cycles over the 8 samples. Over on the right hand side over here, I have the result of multiplying the signal that I'm analysing. So I'm multiplying the signal that I'm analysing up at the top here by each of these basis functions, and the result is being shown over here on the right hand side. Okay. Now what I'd like you to do is relate that to the mathematical expression that you saw. Okay. So this here is x. All these on the right hand side, we have x multiplied by the basis function. Okay, just indicate it like that. And finally, in this column here, over the right hand side, I have the summation of the samples that result from multiplying by x by each of the basis functions. And the interesting thing you should note is that I only get a non-zero value for the case where the signal or the basis function matches the number of cycles of the signal that I'm analysing. So the signal that I'm analysing has 1 complete cycle. I only get a non-zero value when I multiply by this basis function here. Okay. So what the correlation process does, it produces a non-zero value if the signal that I'm analyzing contains the basis function that I multiply the signal by. Okay. For other cases I get values of 0. So let's just confirm that. So by adding these samples together I get a value of 0. Now the reason why I get that is because I've got 3 positive values, and those 3 positive values are cancelled by 3 negative values down here, and then I've also got 2 0 values, so the summation is 0. And you can check that out for all of the examples. We might do one more. So for this multiplication of this by this basis function, we get a positive value, a negative value, and lots of 0 values. But the positive and negative cancel out to give you 0. Okay. So that indicates that the correlation process actually works. Let's just note the actual values that the DFT would return and how they would return them. So my x0 value is the result of summing these values, which is basically x of n multiplied by this sequence of numbers. So that's my x0 value. My imaginary part of capital X0 will be, or my imaginary part of capital X1 will be 0. My real part of capital X1 will be a value of 8. My imaginary part of capital X2 will be 0. My real part of capital X2 will be 0, and so on. I might just rewrite those instead as just simple complex numbers. So that's equal to x0 is equal to 0. x1 will be equal to 0, or rather 8 plus 0j. Okay. x2 will be equal to 0 plus 0j. x3 will be equal to 0 plus 0j, and x4 will be equal to 0 plus 0j. So let's think about how if we were to plot these values, what we would see. Okay, so this is basically our frequency content of the signal. x0 has a value of 0, so bin number 0 has a value of 0. Bin number 1 will have a value of 8. Bin number 2 will have a value of 0, and bin number 3 will have a value of 0, and bin number 4 will have a value of 0. So that's our frequency content based on those numerical values that we obtained. So that's just one example of the DFT in action, and it worked as expected, because remember, the DFT is identifying the presence of sinusoids. We can see that the mathematical process that we followed is showing us the presence of the sinusoid. Okay. Okay. Let's take up another example. Just clear that. Bring up an example with 2 sinusoids instead. So I have a signal here that I've created already, x of n, and in this case the signal that I've synthesized, again I've made it very predictable. It's got 2 sinusoids again. One of the sinusoids is a sine waveform with 1 cycle over 8 samples again, and the second sinusoid is a cosine waveform with 3 cycles over the 8 samples. You can see that they're different in amplitude. And I'm doing the same process. I have my sequence of analysis basis functions, and these basis functions are basically being multiplied by the signal that we're analyzing to give us a result over here on the right hand side. So this is x multiplied by each of the basis functions over here, and here's our result of summing those. So this is our correlation result, if you want to look at it like that. And the correlation result we get, again, it indicates, well, we've only got non-zero values in 2 cases, which is to be expected, because we know what the signal is We know the signal that we're analysing contains two sinusoids, so this just verifies that the mathematical process works. We see that we get a value of 16 when we multiply the signal that we're analysing by a sine wave with one cycle. We see that we get a value of 8 returned when we multiply the signal that we're analysing by a cosine wave with 3 cycles. These values are interesting because we can see that the sine wave is twice the value of the cosine wave, and that corresponds to the sine wave up here being twice the strength of the cosine wave. Okay, so again the correlation process seems to have worked well, and it also indicates well the strength of the sinusoid, the relative strength of each sinusoid. Now, to get the actual value of the amplitude, it seems that we just scale by n over 2. So that is a rule, just remember that. Just scale the value you get back by n over 2. In our case, n is 8, so n over 2 is 4. So scale by 4. So we can see that the sine part has an amplitude of 4, so scale 16 by 4. And we see that the cosine part has an amplitude of 8, so scale by a factor of 4 will give you a value of 2. So the amplitude of the cosine waveform is in fact 2. Okay. Let's maybe quickly run through the values that we get back again. So x0 in this case will be again 0. The imaginary part of x1 is 16. Okay. The real part of x1 is 0. The imaginary part, let's skip the x2, the imaginary part of x3 is, sorry, that should be a 1 up there as well. The imaginary part of x3 is 0, the real part of x3 is 8. Let's just redo those over here. That's just complex numbers. x0 is equal to 0, x1 will be equal to 16j plus 0. x2 will be equal to 0. x3 will be equal to 8 plus 0j. And x4 will be equal to 0. So if we were to plot the magnitudes of these values to show the magnitude spectrum of the signal, what we would see is a value of 0 for bin number 0, a value of 16 for bin number 1, a value of 8 or a value of 0 for bin number 2, and a value of 8 for bin number 3. So it would be half the strength. And a value of 0 for bin number 4. Okay? So let's just clear all that now. That's our second example. Okay. In my third example, I'm going to take a look at a sinusoid with a phase shift. Okay, so the signal that we're going to analyse in this case, again, a known signal, so that we can predict what the DFT should produce. But I have a cosine waveform of amplitude 3. It's got 2 cycles, 2 complete cycles over 8 samples. Again, 8 sample signals, but this time it's got a phase shift. Now, in order to appreciate this example, you need to appreciate that a signal with a phase shift, or a cosine waveform with a phase shift, can be represented in this way. So a cosine with a phase shift can be represented as the sum of a sine wave with no phase shift and a cosine wave with no phase shift. Let me just write that out. So if you have a signal cos omega t plus phi, you can represent that instead mathematically as being cos phi cos omega t multiplied by cos omega t plus j sine sine omega t. I'm pretty sure that's correct. I might be out by a sign or something like that, but it's something like that. Now let's just flick back to that example, which is here. But in this case, so we're dealing with a cosine waveform with a phase shift, which can be represented mathematically as being the sum of a sine and a cosine of the same frequency. In this case, the frequency is 2 complete cycles over 8 samples. And we can see again that we have our basis functions, same as before, and each of the basis functions is being multiplied by the signal that we're analysing. So x is multiplied by the basis function over here on the right, and we're summing the result, which is basically our correlation value. And once again, the DFT analysis process is working well. We're getting a value of 0 anytime the basis function isn't present in the signal that we're analysing. Now we're getting non-zero values again for the case where we have a signal that has 2 cycles over n samples. So in both cases here, our basis functions have 2 cycles over the n samples, or in this case 8 samples. Now the actual values that we get back are 10.61 and 5.6. So remember, we have to scale those by a factor of 4 to get our actual values. So let's just bring those into MATLAB. Well, actually, let me go back. Sorry. There we go. What I want to do before I just show you those in MATLAB is we'll write out the DFT values that we'll get back again. So I don't think I need to go through the real and imaginary parts again, but just let's say that x0 will be equal to 0, x1 will be equal to x1 will be equal to 0, x2 won't be equal to 0. Sorry, something just happened to my pen. I need to flick it back. Okay, so x2 will be equal to 5.6 plus 10.61j. Okay, x3 will be equal to 0, x4 will be equal to 0. Okay, so again, just looking at the magnitude spectrum, what we'd get is a lot of 0 values for bin numbers 0 and 1. Bin number 2 will have a non-zero value, and bin number 3 and 4 will be 0 values. Now the values that we actually get back, if we write them out in MATLAB now, so we have 5.6, that needs to be scaled by a factor of 4, plus 10.61 scaled by a factor of 4, j. That's the value that we get back. And if we took the magnitude of that, ABS, we get a value of 2.993, and now there's a little bit of rounding going on, but we see that the amplitude of the cosine waveform was 3. And we'll also see, if I've done my calculations correctly, that if we take the angle of that, we should get a value of minus 1.0852. And I feel I've done something wrong there. Not absolutely confident about what I've done there. Something amiss. But the general idea seems correct. The whole idea, of course, is that the DFT is identifying the presence of sinusoids, and it's doing that well. And it'll work for either sines or cosine waveforms. Okay, so the key thing about this video was to try and understand the mathematical expression and what's going on, okay, and how it actually does what it's doing. Now, all the examples that I've used so far have all been dealing with signals that were made up of cosine waves or sine waves that had an integer number of cycles. Now the real difficulty with the DFT in practice comes when you're dealing with, well, signals that don't have integer number of cycles. And I have just one last example that I want to show you. And I'm not going to go I'm going to put together another video to deal with what's known as spectral leakage and spectral spreading. But it's an issue that arises. I just want to clear that. It's an issue that arises when you're analysing signals that don't have integer number of cycles. So in this example that I have here, I have created a sinusoid again. It's a pure sinusoid, but it has got 2.3 cycles over n samples. And what happens in that case is we don't have an exact match of the signal that we're analysing with the basis functions. So in all the other examples that I did, we had exact matches, but we don't have an exact match now. And what we do see is we get a sequence of numbers back. Here are those sequence of numbers. Now the thing to note about the sequence of numbers that we get back from our DFT analysis is that we get large non-zero values for the case where the signal that we're analysing is most similar to the basis functions. So this signal that we're analysing is 2.3 cycles. We get a lot of similarity with these two basis functions, okay, indicated by these values here. Okay, we get less similarity for the other sets of basis functions. So this is the set associated with k equal to 1. This is the set associated with k equal to 3. And we see that we get smaller values for each of those cases. I'll just try to plot the DFT of that. I just need to clear something. It's going to take me a little second. Just bear with me. Can I just delete that? No. There we go. Okay. So I might just try to sketch out the magnitude spectrum of that. Okay. So let's just write out what the x values will be. x0 will be minus 2.46 plus, oh sorry, I've done that wrong. x0 will be equal to 5.15. x1 will be equal to 5.73 minus, oh, hold on, that should be plus because it's a minus in the formula, and that's where I was getting wrong that's where I was getting confused in my previous example, but you can change those signs later on. Plus 4.6j. x2 will be equal to 13.18 plus 14.02j. x3 will be equal to 4.8, sorry, mixing these values up again. So it'll be equal to minus 1.61 minus 4.89j. And x4 will be equal to, just reading over here of course, equal to 0.26. Okay, so we have all these values that we get back, and let's just plot the magnitude spectrum of that. Just quickly sketch it, just to show you what you would see. You'll see for bin number 2, we're going to get a significant value. Bin number 1, less, and bin number 0, smaller again. Okay. Bin number 3 will be less than bin number 2, and bin number 4 will be smaller again than bin number 3. You get this, what's referred to as spectral spreading. And I'm going to put together a video that describes spectral spreading in a little bit more detail, and also techniques to not reduce it, but to make the results of spectral spreading more predictable. Okay, I realise that's quite a bit in that video, mainly due to the fact that the DFT is quite complex. Hope it all made sense, and thanks for your attention.